standards, AV1, VVC, and AI-assisted encoder implementations. This session will be moderated by Mark Donnigan. Mark leads the market development efforts at Visionular, a company building advanced video technology. Mark is a veteran of the video ecosystem, having worked with disruptive innovation companies to increase video codec and streaming technology standards adoption. Mark, it's great to have you here. Throughout the talk, I'd like to encourage the audience to put any questions in the questions tab to the right of your screen, and we'll try to get to those towards the end of the session. Mark, the floor is yours.
Excellent. Well, thank you, Max. Super excited to be here. Thank you for joining us. So the title speaks for itself. Understanding the latest video codec standards. It's a huge topic. It's a bit bewildering at times, and so we really hope that over this next hour that we're going to be able to unpack and maybe provide some clarity as to specifically what's happening in AV1, VVC, and not exactly a codec standard, but we will be touching on AI and machine learning assisted encoder implementations, as I think this is becoming a much greater part of the video ecosystem, and certainly a topic that I'm sure many of you are interested in. So here's the goals for the session. Really pretty simple. Number one, myself and the panelists would like you to walk away and say, wow, it is possible to move to an advanced codec standard. Again, the decisions are very complex. There's a lot of considerations, but hopefully you're going to leave this session, and that's going to be one of the main takeaways, is that it's possible. We don't need to be planning for 5 years in the future. Maybe we can be planning in a much closer time frame. The second is relative to the subject of real-time communications, real-time experiences, RTE, is that advanced codecs can support real-time video. So throughout, we're going to be heavily focused. We will be talking about VOD applications, but largely we're going to be focused on live, low latency type applications and use cases. So with that, let's get started. And I would like the panelists to go ahead and introduce themselves and tell us where you're from, who you work for, and what you do. Let's go ahead and start with Jan.
All right. Thanks, everyone. My name is Jan de Kok. I'm director for codec development at Synamedia. I'm based out of Belgium. Now, Synamedia is a global provider of video and networking solutions. We provide the entire chain of encoding, packaging, delivery, all the way to the CDN. Yeah, this is strongly related, of course, with the, let's say, real-time experience that we'll be talking about today. So glad to be part of this panel here.
All right. Thank you. So I am not going in any particular order here, guys, so I apologize for that. Shawn, I'll go ahead and why don't you introduce yourself?
Good morning, everyone. Yeah, my name is Shawn Zhong. I work for Agora. Agora is an active proponent for real-time engagement, and we provide a platform as a service solution for real-time engagement. And yeah, it's great that we have this opportunity to discuss advanced video codec for real-time engagement. Thank you.
Excellent. Thank you. And we certainly thank Agora for putting on this event. Debargha?
Okay, good morning. So my name is Debargha. I work for Google. So I'm a principal engineer in Google, and right now I'm looking at next generation video codec technologies, which could potentially be a next gen AOM codec. Prior to that, I have led the AV1 algorithmic development efforts from Google side, and prior to that, I worked on VP9. So these are, and so our team is a very big proponent of royalty-free ecosystems and codecs, and our plan is to continue doing that as long as we can. Yeah, and happy to be part of this panel and take part in the discussions.
Excellent. Thank you very much. And certainly last but not least, Tarek.
Thanks, Mark. Thanks, everyone. Good morning, everyone. My name is Tarek Amara. I'm the engineering manager for the video transcoding team at Twitch. Twitch, for those who don't know it, is one of the biggest live streaming platform covering gaming, entertainment, day-to-day experiences, and new applications as well. This team is mainly focused on enabling better video delivery at lower cost, at scale, at low latency, at lots of other competing goals against each other. We are also the team behind the IVS, the Interactive Video Services, which is a year-old now, new service enabling developers and other companies and simplifying and facilitating live streaming for those. So I'm super excited to be here.
It's excellent. We're happy to have you. Well, I'd like to start. We've prepared a couple slides here that we are going to go over. And just to set the stage of exactly where we are in the development of this multi-codec world. And so, Jan, you put a couple slides together, and then we're going to have Debargha and with an overview of the AV1 ecosystem. A lot of really up-to-date information here. So, Jan.
Yeah, thanks, Mark. So this is a visualization that I'd like to use just to illustrate the adoption of the different formats. As you know, there are plenty of formats out there for video compression. And we're going through different stages. But actually let's say, fragmentation in this multi-codec world is increasing. And actually, it's also accelerating. Now, what you see here on this slide, and I'll just go through the highlights here, is on the left side, a depiction of the broadcast situation. The broadcast world typically has been evolving a bit more slowly. It's more hardware driven, so there's a lot of install base. It takes a bit longer. In any case, at the moment, at the top left, this is more or less the situation today, where you see that AVC is still occupying the bulk of the traffic there. MPEG-2, it's a very old standard, more than 25 years old, but it's still out there. And even these days, you would see new deployments for MPEG-2. But in any case, you also see HVC coming up. There's some momentum there. So it's slowly evolving. And at the bottom left, you see projections for the coming 3 to 5 years where HVC is slowly growing. But you also see new contenders coming up. And today we'll be talking about VVC, which is, I would say, could be, a successor to HVC, but also maybe AV1 can pick up in the broadcast world. On the right side then, this is the OTT delivery space, where typically innovation goes faster, there's more software deployments, where you see that there's already more fragmentation. AVC is still very big out there, but you already have HVC, and you also have royalty-free formats. The momentum is really there for VP9 a couple of years ago, but now also AV1 is already becoming bigger and bigger. And as we'll be talking about also that AV1, there's plenty of deployments, there's plenty of encoders, decoders out there that allow it to be deployed widely. In a couple of years, I would say AV1 will continue to grow. We'll also see how VVC is doing, and how the licensing situation will turn out there. But this is roughly, I would say, how we can expect the situation to evolve. Yeah. Don't quote me on the measurements on these graphs and the numbers, but these would roughly indicate the tendencies. So that's for the first slide. Thanks, Mark. And then on the second slide, I tried to summarize the situation or the status for the different formats. Tarek, you might recognize this is actually based on a slide that I saw from you at Streaming Media, slightly updated. So feel free to correct me here or jump in. But these are, I would say, the biggest formats out there now, ranging from AVC over HVC, but also VP9, AV1. And then there's a couple new formats that were standardized last year: VVC, LCVC, and EVC. Now, there's still some question marks, definitely at the bottom. But what you see also in terms of compression efficiency, there's several interesting contenders, AV1 and VVC again, that are ready to be used. You also see more and more encoders, also open source encoders being made available. and shared, and you can see them on the right-hand side. But also what's interesting is that formats like VP9 and now also AV1 already have quite some support on browsers, CE devices, and also important for today, real-time support, for example, on RTP and WebRTC. So yeah, we'll probably will likely also come back to that later on in this panel.
Yes, we will. Excellent. Thank you, Jan. Okay, Debargha, how is AV1 developing?
Yeah, so this is kind of like the time when we are 3 years after the initial release of AV1. So it's a good time to actually look at what the proliferation of different software services and hardware has been. So this slide has 4 sections. I just put in a lot of the logos of different devices and different services that are using AV1 today. So Windows, in terms of software support, we have Windows 10, Chrome, Android, and it's supported on browsers, the Firefox, Chrome. Chrome was obviously one of the first to support AV1 decoding, Edge, then VideoLAN. In terms of web services, YouTube, again, being one of the first to start using AV1. Now it's slowly coming into Netflix and Facebook and Qi. And then in terms of real-time services, we have Duo and Cisco WebEx starting to use AV1 also. In terms of hardware adoption, we have for desktop chips, the chips from NVIDIA, MediaTek, AMD, and Intel that are supporting AV1. In the smart TV space, I think this year is the year where we actually have a lot of TV models that are supporting AV1, like from LG, Sony, Samsung, TCL, Toshiba, Vizio, and in terms of streaming boxes, Roku supports AV1 as well. And in smartphones, we have Samsung phones that support AV1, the Xiaomi and Vivo and Oppo also starting to support AV1. So this is in a very a brief nutshell of the adoption, and all of these are set to grow over the next year or so.
Yes, they really are. Well, that's excellent. Thank you. Well, thank you, Jan. Thank you, Debargha, for the overview there. And so hopefully that helps for those that maybe are not able to monitor the emerging situation, specifically around AV1, but also VVC and some of the other standards. So I just want to jump right into the conversation. This is why we're here, and I really can't wait to facilitate this talk. And I think a really good place for us to begin is to discuss and have some conversation around what are the steps that need to be completed when you're beginning to think about how to compare codecs. And so this is going to be kind of a free-for-all question here. So I'll let kind of the first person to jump in begin to talk about this. But panelists, if you could, give your thoughts around how should someone even approach evaluating a codec, thinking about AV1 versus VVC, or maybe they've not even migrated yet to HEVC and thinking about that. And then also codec implementations, because I think it's very important that we not just focus on the codec, but we think about the actual encoder implementations. So let's throw it out there. And who wants to jump in and give some thinking around this?
I'm probably happy to share how we look at this and how it's a very tough question, by the way. Yes. There is no one way to do it. It really depends on how you want to approach it. The way we approach, at least, is very, very business driven. So obviously delivering better quality of service, lower bit rates, is definitely everyone's goal, or most of people's goal as well, in addition to delivering new features, lower latency, and those kind of stuff. The way we look at this is, number one is we're not arguing the compression savings, because there is no reason for us moving to a new codec without compression savings. And the challenge for us, at least, we are a real-time application, and this is basically probably the focus of this panel. We need to achieve real-time at scale, and that's super challenging. So the way I'm looking at this from an encoding point of view is where the industry stands, what is everyone doing, What are the capability? Is this number one, is this codec capable of delivering real time at a reasonable cost for a scalable solution for hundreds of thousands or maybe tens of hundreds of thousands of channels concurrently? That's one part of it. I don't want to jump the gun a little bit on talking about ecosystem as well, because adopting a solution, you can have the best solution in the world. You can say 50% of the bits, and it is very cheap to deploy. But if people cannot watch it, if it doesn't have enough reach, and this is more of the ecosystem support, it's something we would like to see happening as we identify, yes, codec are fit from a broadcast or a distribution point of view. The other complementary side, which is always a need, is does the ecosystem and is the delivery ready to start consuming that codec?
Excellent. What else?
Yeah, and Mark, I also like to share a few observations and experiences we have in selecting the codec. And first, evaluating the coding formats, coding standard is very different from evaluating a codec selection for RTC or RTE usage, because the real RTE environment is very challenging. The transmission network has to be considered. The network itself is with packet loss, and sometimes with a packet loss rate as high as 80%. We saw that more often than not. So the codec used for RTE has to be packet loss resilient and also of low latency. And because the network is also congested very often, and it's jittery as well. So the video coding will need to give very good quality of experience from end-to-end transmission, especially when the network condition is changing and challenging. So we need to take into the consideration of the network status, and we need to have a way to detecting the network status. For example, its bandwidth, available bandwidth. When the bandwidth varies, we need to be able to adapt the video codec so that some kind of scalability can be built into the encoder implementation. And all those factors are actually in addition to the traditional evaluation for the codec, which is only about like the coding gain and the complexity. The coding gain and the complexity is also very important, but we have to consider other factors as well. And another important factor we need to consider is the wide support by the devices, either especially by the mobile devices. There are a lot of all kinds of mobile devices, and supporting a codec could mean a hardware support or a software support. For hardware support, it basically means the SoC chips inside the mobile devices need to support the codec. And by software support, it basically means, especially for the encoding, it has to be simple enough to be able to run in real time by the CPUs in the mobile devices. So it's a very evolving and complicated process for evaluation. Later on, the user experience also depends on like the display devices as well. So there are a lot of factors to evaluate this. Mark?
Yeah, thank you for pointing that out, Shawn. You know, one of the things that comes to mind with what you just said is really being mindful of what the use case is, what the device ecosystem is, because adopting a codec is as much about the application as it is about the performance or the benefits of the codec. And so, you know, I'm curious if somebody else can jump in and maybe give some color around where the MPEG codecs stand in terms of the types of devices that they typically are supported on, and where the VP8, VP9, AV1, kind of the Google onto where those fit, because they do look pretty different. The device ecosystems are pretty different, and I think it's important for us to talk about.
Yeah. Mark, I can maybe jump in here, but I have other experts here, and there are other experts here on the panel as well on the ecosystem side. But indeed, the first step in determining your format is really looking at, who do you want to reach? Because as you said, there are very different, let's say, deployments for the different formats. And you saw it a bit on the first slide as well, like AVC used to be this almost exceptional success in terms of deployment. It was it's on billions of devices. It's on all major browsers. It's on all, let's say, supported on pretty much everywhere. Now, after AVC, you have more efficient formats, but they're not supported everywhere. You have VP9 was deployed more on Android, Chrome and Firefox. On the other side, you have HEVC, which is enabled on Edge, Microsoft Edge, for example, but not on other major browsers. It is enabled, though, on iOS devices. So you have the split up also in CE devices between Android and iOS. And this is one of the major factors that also will determine which formats, which standards you want to deploy. And in the past, it was easy. I mean, you had AVC. Now it's also this, you will go for perhaps HEVC for certain premium content. You would see that on Netflix and Disney+. But on the Android side, on certain browsers, you would be using VP9. And more now, you would be using AV1 because AV1 is also ready for prime time. So it's a bit of a complex puzzle that you should solve first in terms of reach of the devices. So that's indeed the first step, even before you start selecting encoders.
Excellent.
Yeah,
very good point.
Let me add a little bit of to what the complexity aspect of an encoder that was touched a while back. I think there's a big difference between releasing a codec for VOD applications and releasing a codec for deployment in a real-time conferencing application, because in a largely how the system, the codec behaves in a system depends on the amount of computation you can do. So in today's codecs like AV1, VVC, or even HEVC, the search space is so huge. In a real-time application, you can never search that. So whether you really get the benefit out of deploying a new codec versus a previous generation codec depends to a large extent on the smartness you can put in on the encoder side. So without that smartness, you'd probably be about the same as H.264 or like an older codec. So I think what we have been seeing is like between a codec being released, a codec format being released, and the time when it actually can be used in a real-time conferencing application, is usually 2 to 3 years of development and research cycle that needs to be spent on it. Now, of course, I think that's the way that things have been going, but it is potentially possible that we could probably change the way we standardize codecs. And if we did that, maybe that time to market for real-time codecs can actually be shorter. But it's a difficult problem to get everybody on board to really agree to having, let's say, 2 different codecs standardized at the same time, or maybe have one codec being a subset of a larger bitstream syntax. That's the thought I had on real-time codecs and deployment.
Yeah, that's excellent. Thank you. All amazing comments, and thank you for your observations there. Maybe this also is a good time to talk a little bit about the role of the decoder. And I'm thinking from a little bit of a different perspective. Obviously, we care about devices that can decode the bit streams. And that's already been mentioned. But I'm wondering if any of you have some comments when it comes to actually optimizing the encoder. Is it possible to also that there's some optimization that can be done or should be done in the encoder to facilitate better, smoother, maybe lower power consumption decode playback? And so I guess, throw this question out there. What is the role of the decoder when we're talking about optimizing these new much more advanced codec standards?
So if I can start off with that. So initially, when, let's say, as to give an example from VP9 and AV1 that we have seen in the last few years, like right after the bitstream is frozen, it's always very easy to release, or it's much easier to release codecs that can be decoded in software.
Yeah.
So when you're decoding, let's say, AV1 or VP9 in software, and you want to make sure that the browser can actually keep up and play back, let's say, 4K, 60, and so on, we do definitely need to do a lot of tricks on the encoder side, actually turn off certain tools that are harder to decode to really keep up the throughput. So that we routinely do. But as hardware becomes available and hardware support becomes more ubiquitous, then I think that pressure releases. So we can actually use all the set of tools that the format supports. Now, that's only up to a point. Let's say if we are getting to the stage of, let's say, VVC or AV2 or AV next, or whatever the name of the next AOM codec would be if it happens. There, let's say if we use tools that are much more complex to decode than traditional codecs, let's say if we use a ML-based tool, then I think it could be a problem. So it may not be possible to actually support decoding that in software, period, if we have those tools enabled in the profile. But we are kind of a few years away from that stage. So far, until AV1 or VVC, it seems we should be able to get the software decoding throughput up to 4K. VVC, I'm not quite sure yet, but maybe yes. Everyone certainly, yes.
I'll add to what you said, Deborah, because we went through a similar experience when we started using VP9 as well. However, I'd like to take one step back is we start seeing more and more hardware people in the standardization groups, and that's for this specific reason, so that when people suggest new features or new tools for the encoding, we know that the decoding or the implementation of those features on the decoder side are reasonably feasible and reasonably doable within a reasonable time frame with the current or next generation technology or silicon capabilities. So that is taken care of early enough. But obviously, even after the encoder release, there is challenges to make sure those things happen, right? So there is kind of a check at every single step of adding new tools or features during the development process of the standards. However, I feel it's true that sometimes, for software development, it's really hard, and I echo what Deborah just said. It's really hard to have all these features supported. So going with the subset, the challenge there becomes how much compression efficiency. Would I be interested on deploying an AV1 where you have cut 10 or 20 of the main features that give me the compression savings? And that's kind of the balance where engineering teams, when they try to implement an encoder, try to kind of segregate. And in general, this is a little challenging because you won't always find coordination between people who are writing the decoders and people who are writing the encoders. These in general are different teams, right? So unless these are a very limited set of features, I remember VP9 has got like the tiling enabled in the first few days, right? And number of reference frames as well. Going deep into the details, but that was kind of one way to get it out of the way, but now it's the full set of features in the spec are enabled. So that's the ultimate goal. But would it be a facilitated number of steps? It's super challenging, but definitely it's a way forward, yes, to enable faster deployment.
There's one feature that comes to mind that I think really illustrates what we're saying here and what you just said, and what both of you said is scalable, SVC, scalable video coding, or the ability to adjust temporal rates, that's in HEVC, right? In the HEVC standard, but it's not required and it's not implemented, or rarely implemented on the player side. And yet it's an incredibly valuable feature in real-time communication specifically, and it is in the standard and required and supported by the decoders, by the players in AV1, right? So there's some specific, tools and even features of these codecs, which when they're first published and everybody's excited about it, everybody talks about it, but then you look at what actually is deployed, and you can be sort of let down a little bit, and that can be in the form of compression efficiency that doesn't live up to the gains that we hope to get, or just features that sure, I can implement it, but it's not going to play back everywhere. The bit stream's not going to be compatible. So.
I also like to share a couple of examples of how we jointly optimize the encoding and the decoding. So making use of the decoder side information for some encoder side decision making greatly benefits the whole end-to-end user experience. One typical example is that we can select a reference picture based on the feedback message from the decoder. So this way, we are always guaranteed at the decoder side, the reference picture is always available so that decoding can be always carried on. Otherwise, when the reference picture is lost, then the decoding would be broken. This is example one. Another example is that we also consider factors like the computation power of the receiving device, as well as the network condition, so that we can make decisions on the encoder side, what is resolution, if we can reduce the resolution of the video or reduce the frame rate of the video to be encoded. Then at the decoder side, we can actually make use of other compensation tools such as super resolution or frame rate interpolation to increase the video quality or frame rate, so that at the decoder side, we can get the user experiences back to a better level, even though the network condition is challenging. So decisions like this, based on both decoder side and encoder side information, greatly benefit the whole end-to-end system. And also, as Mark commented, the scalability is also a way to build into the bitstream, so that when the downlink bandwidth is limited, we can just send part of the bitstream in terms of the temporal scalability to the receiver, while another receiver which have a good bandwidth would receive the whole bitstream, so that it adaptively dispatch the bitstreams to the receiver. All those are great examples of how the whole system can be optimized jointly.
Yeah, it's great. Why don't we talk about the state of, and I guess we can start with AV1 or VVC, doesn't really matter. But let's go ahead and start with VVC, and let's just talk about the state of VVC. So where are we at? Has anybody done testing? I think we would all be interested, even the panelists, to hear maybe what some preliminary findings are in terms of efficiency gains over HEVC or over AV1, if you have that data, and any other information that might be relevant or useful.
Yeah, I can go first. I think in the year before last, I think right after AV1 was finalized and VVC was not yet finalized, we had done some tests comparing AV1 versus VVC and HEVC. And so at that time, there was no really good implementation. So AV1 had a common test conditions, which is very different from the common test conditions used in MPEG. So it's very hard to do an apples to apples comparison. But what we did was we took the best implementation of AV1 and the best implementation of VVC, which was some version of VTM at that time. and then compared, and then VVC did turn out to be better in a VOD scenario, like at the full complexity and all that. And then at this, so now going forward in 2020, early 2021, we did some tests with the latest VTM compared to AV1 and VVC. And in our opinion, in the best possible way, we can match the parameters to match the common test conditions. AV1 seems right in the middle of between HEVC and VVC in terms of coding efficiency. So that's our best guesstimate so far. But there's some work that is going on in the broadcast side on 3GPP and DVB and all that to get a really good handle on that. But that's our best estimate so far in terms of performance in a VOD use case when you have full complexity. Yeah. Now the real-time usage is I think we don't have enough data on that for VVC.
Understand. And just for completeness, were you testing Debargha with LibOM? Was it probably not LibOM RT, but LibOM, yes, or LibOM. Which implementation?
LibOM, which is the slowest speed or speed 0, compared to VTM.
Okay.
I believe the 6 point some version. Yeah.
Okay. Do you recall by chance even some basic numbers of what the encoding times were, the differences were between, AV1 and VVC?
Or
VVC, did you normalize for encoding time?
We didn't. We just ran the best possible way we can run VTM and best possible way we can run AV1 while matching the common test conditions as much as possible. And at the time we tested, VTM was way slower than LibOM, but I don't. It's just. I think it's a state of development of VVC, maybe course. More behind. Yeah.
Of course. Yeah. Okay.
Yeah, I think it's a pretty fair statement, what Debargha said about AV1 being somewhat in the middle between HEVC and VVC. That's also my observation. Recent publications report about, depending on the conditions, between 25 and 40% for VVC, more or less. That's between both reference software packages. And AV1, we've also measured to be somewhere in the middle, 15, 20, 25%, depending on the settings. It's indeed a bit of the question how much this will change when you go to real time, because for AV1, we've seen very good encoders. LibOM is out there, SVT AV1 is out there, but you also have proprietary encoders. If you look at the Moscow State University results, there's some interesting encoders out there as well that can also handle real time at high resolutions. So there's quite some interesting results out there also for real time. For VVC, we've tried the VV-Enc encoder, which is available open source. It is much faster, or you can run it much faster at least than the reference software. It's like a factor of 100x if you give up some of the gains. But it's not. Real time. It's not yet fully there yet. So it's hard to compare, let's say, VVC and AV1 at that point. So we're looking forward to. We're also working on that, and we're looking forward to showing more results about that in the near future.
Yeah, thanks. I also feel like for real time, when you're getting to the stage of real time, I think what starts mattering more is really how you optimize the encoder, and rather than the actual bitstream syntax.
I want to follow up on that actually. The out-of-the-box comparison without taking consideration of the performance of the cycles consumed is important when we come to say, ultimately, the best ever AV1 versus VVC encoder, what is the delta here from a pure research and technology point of view? When we come to RTE, which is the purpose of this conference, can it be done within the reasonable cost? Can it be done within a reasonable set of cycles? It's true that when AV1 came in a couple years back, it was super slow. LibAOM was kind of the only version out there, and people were kind of saying, no, there is no way for this to get anywhere near real-time applications, right? So it was a joke. I was in MPEG conferences and people kind of were making fun of the speed. However, over the last couple of years, we have seen phenomenal jumps, as VVC has already made improvement, VV-Inc have made improvement for VVC. We are seeing AV1 encoders running real-time software today. And I think, Mark, you can probably speak to that for the whole hour. But even SVT AV1 has made huge improvement. LibAOM have made a massive jump. Obviously, this comes at a compression efficiency cost, right? However, these are still showing substantial benefits. One piece of data I want to briefly share, and this was publicly published recently. The advantage of SVT AV1 and other AV1 encoders is they started running at a comparable cost, at a comparable number of cycles as AVC today. So if you take the cost of AVC today, you have a platform running some AVC encoders. You can still run AV1. I'm not going to say real time, but at a fast enough speed that you can definitely see some benefit on existing platforms and technology. VVC came in late, it's probably a year old now, and definitely make some progress, but it will take time. And I think the delta of when the standard came out will make a little difference in terms of deployment and market share as well, which we'll see hopefully happening in the next few years.
That's great.
Yeah, I also like to share one data point. When we're selecting evaluating the H.264 video codec, and one of the commonly used code base is X264, where we think the most feasible speed level of X264 is at the very fast speed level. The median is still way too complex. So let's say something about how excruciating the requirements for the simplicity of the encoder is. And having said that, we're seeing implementations of AV1 is approaching only 4 to 5 times as complex as the X264 at very fast speed level. So if it could go down further to 2x or to 3x as much complexity, then it's very likely can be used in a lot of use cases for real-time communication, real-time engagement. Yeah, we see the light of the tunnel in this direction. And history has said that smart algorithm would progress as time goes on. So is with the CPU capability. So when both this are improved enough, then we will see real-time applications of the AV1 encoder.
Yeah, that's a great comment. And I'm curious, do the panelists agree, do the rest of you agree with what Shawn just said, that when you get to a complexity of, say, 2 to maybe at most 3x, that's kind of the tipping point of when you really could consider adopting, certainly at least for real time and at scale, an advanced codec? Do you all agree with that, or how do you think about that?
For me, at least, it's a cost factor, right? If 2x is going to save me 2y in delivery cost, it's about how the heat will balance. But I definitely agree in a scalable platform. I'm sure Shawn is going through the same challenges. We have hundreds of thousands of concurrent channels. You're offering these transcodes to a single viewer, right? Sometimes for a specific application. So the cost is key here to be able to offer this technology to viewers. So if you have a channel with low viewership and you still need to transcode, it must justify the cost, right? Yeah. So definitely any increase is important. I cannot say whether 2x or 3x is important, but definitely, as he mentioned, X264 very fast is very well deployed in the industry today. And that's a preset that people are surviving with. Increasing that, doubling that becomes a challenge, and you need to justify it.
Got it.
Right.
Got it.
So for us, we care about the software implementation of the standard, because in software implementation, we are able to, as I just said, we're able to combine a lot of information from the decoder side, from the network. So software implementation would provide a lot of flexibility or programmability to provide better quality of experience. So that's why we emphasize the simplicity of an encoder. Meanwhile, we still would expect like about 50% more coding efficiency compared with the H.264 at the very fast speed level. I mean, X264.
What is the role of hardware in this discussion? Hardware for encoding, hardware encoders.
Hardware encoding definitely has some benefits as well. First, hardware acceleration usually is less power consuming. So the hardware encoding or codec can actually is a good thing for mobile devices because of its less power consumption. Yeah, so we need to come up with a strategy of switching back and forth between hardware encoder and the software encoder. Depends on the battery level, or depends on the capability of the hardware. So we have those kind of auto adjust mechanisms built in to decide whether or when to use the hardware encoding or software encoding.
Yeah, I think about that, I think one thing I wanted to add is, so when you, even for a software encoder, it seems like it takes 2 to 3 years to actually optimize a full-blown codec, a new codec, and to make it usable for real-time applications. And to find the right algorithm that can actually search this huge space in a very efficient way. Now, the hardware encoders also have the same problem. Plus, you have the additional time that you need to spend for the silicon and all that. There are some differences because you can search certain things in parallel much more easily and things like that. But otherwise, some of the algorithm changes or improvements will still be needed for hardware. So typically what happens is the hardware encoders kind of evolve maybe at least 3 to 4 years after a bitstream has been finalized for a codec. And now that's almost about the time when we are thinking of a next-gen codec. So I think there's always this delay that happens. So that's the reason why I am of the opinion that actually to reduce that time for adoption, I think the entire way we standardize codecs probably needs overhaul and rethink. Like whenever from a bitstream is finalized to the time it can actually be used for software and hardware applications, that can be much smaller if the way we standardize codecs and evaluate codecs during development is changed fundamentally.
I think there's definitely, a different in use case, right? You see, there are use cases for both hardware and software. So I can imagine also for massive scale deployments that hardware can definitely give advantages. But what we like about software as well is just the flexibility in deployment. You can deploy anywhere on commonly available CPUs in the cloud, anywhere you want. Also, the agility of development, how fast you can get to, good encoder improvements and adoption. And also the flexibility in adding features, for example. You're less bound to your hardware. You can more easily add features into your pipeline, new algorithms, new innovation. Although I am impressed by how fast some of these recent hardware announcements have been made, for example, for AV1. But I see benefits to both cases for sure.
Yeah, excellent. Well, good. Well, we could spend more time, but I want to make sure we get to AI and machine learning. We talked about how, that also is becoming a really important and valuable part of this whole discussion. So let's jump in. And when we were preparing for this talk, I know that all of you had some really interesting insights. And so I'm just gonna throw it out there. And again, whoever wants to jump in and start sharing your thoughts, what you're doing, what you're seeing, and let's just keep it focused on, where can AI and machine learning today? So it's great to talk about the future, but where today can using artificial intelligence and machine learning approaches, in the codec really bring benefits?
Yeah. Oh, sorry. Shawn, you want to go first or what? Okay.
Go ahead, please.
Okay. Yeah, I mean, AI, it's a very popular topic, of course. And we get a lot of questions around it. There's a lot of announcements around it. I often have to like adjust the expectations around AI because like algorithms or neural networks, deep neural networks, and so on, it's one thing. Applying them in encoding and definitely in real-time encoding is another thing. If you look at many of these networks, they have dozens of layers with millions of multiplications going on. I mean, just replacing some algorithm in your encoder by this deep neural network, it's not going to work, or the cost of encoding is just going to explode massively. So you have to be very mindful of where you apply it. Definitely in real-time encoding, you want to be looking for heavily optimized algorithms that limit the number of multiplications, for example. And then, yeah, you want to maybe minimize the footprint by pruning the networks, by quantizing, let's say the depth of your multiplications, your operands, and so on. So I mean, there's a lot of deep knowledge both on the codec side, and the machine learning side, and the optimization going on. But once you combine that, I do believe that there are several areas where AI can help us, and we've seen that, for example, in making our encoders more flexible, more content aware, improving our bit prediction for rate control, for example. Another important area that not only that we've seen, but also that I've seen announcement on is around pre-processing, for example, pre-processing, post-processing, something that these algorithms are particularly suited for. So there's quite some areas where it can help, but you have to be very mindful of the complexity. And fortunately, also in standardization bodies, there's definitely a tendency to focus a lot on that complexity, so we don't like screw up the people that have to implement it later on. There's definitely awareness that it can be very costly. So that's a good trend.
Right. John is definitely correct to point out that we have to be mindful when we design a deep learning algorithm to help video encoding. We have actually come up with quite a few deep learning models for the mobile devices. For example, super resolution is one, and the frame rate interpolation is another. And also we have designed a CNN, convolutional network-based perceptual video coding strategy, which basically captures the human visual perception for the distortion, because our eyes are sensitive to some distortions, while not so sensitive to other distortions, especially for areas with very complicated textures. Distortions is not that visible, so we can take advantage of this by designing a very small deep learning models. So the few deep learning models I just mentioned, the number of parameters is just in the range of a few K parameters, unlike the usual deep learning models which have millions of parameters. So this greatly reduced deep learning models is actually executed in real time in almost a wide range of mobile devices, high-end, middle-end. Some of them can be even implemented on low-end mobile devices. For example, the perceptual video coding model I just mentioned can do like 1720p frame encoding for very low-end mobile devices. And also, we also have make use of machine learning and deep learning for standard compliant B-stream generation, as a few examples for the mode decision, for the block partition decision, as well as the bitrate control, as Zhong pointed out. And even amazing that for scenarios like usage cases like this, we are trying to convey the most important information that the first frame of a person is already conveys identity information is already there. So the next would be like, we would be able to transmit a few key points, visual key points. Then we can make use of the visual key points to generate or reconstruct the video based on the identity information from the first frame. So those kind of technology is already there, and from the generative deep learning models like the GAN, the generative adversarial network, the variational autoencoder, all those things actually can help achieve the intention I just mentioned. So the question is how small we can design the model so that it can be executed on mobile devices. So stuff like this are very exciting and very promising. Mark?
Well, maybe next year this panel should just be solely focused on AI and ML, because I feel like we really didn't get into the meat of the topic, and there's just so much exciting development happening there. So we are looking at the clock here. We're 5 minutes to the top of the hour, and we do need to keep on schedule. If there are any questions, I encourage you to just go to the question box. I believe that we don't want to use the chat just because it can get kind of cluttered up, but go to the question box and put a question in there, and we would love to address it as we have time. I think, to close, there are some questions here which were answered. Thank you, Debargha. I know you jumped in here, but I think it's probably relevant to everybody. So I'm going to go ahead and read through some of these, and then we can see what else comes in. But there's a question about what about Apple OS X and iOS? And I am inferring as I read through that this person is asking about AV1 support in the Apple ecosystem. I guess I can answer that one really quick
Sure.
because it's public. Apple is a founding member of the Alliance for Open Media. Obviously, Apple, like really all companies, but as we know, Apple's even a little more tighter-lipped. They don't divulge their roadmaps. So I don't think anyone on this call would be prepared or even able to try and offer any future guidance. But considering that Apple is a founding member of the Alliance for Open Media, you can infer that they have a lot of things to be working on, and if they weren't interested, they probably wouldn't be a member and participating. Does anybody else have anything to add? Debargha, do you want to jump in there? Or?
Oh, yeah. So I think the only one thing I wanted to add is, yes, so we don't know anything public about Apple, but I think one thing is, I think for the next gen work that is going on in the AOM work group, I think Apple is very, very involved, and we have seen several.
And you're speaking of AV2 specifically,
yep.
Right? Yeah. Yes, that is correct. Okay, let's see. How does AV1 compare to the older codecs for under 4K streams? So basically lower resolution, I guess you could say HD and then SD, and especially considering the computational expense. So that's actually a great question.
Yeah.
Who wants to?
Yeah. So I can give you a little bit of, it's not an easy question to answer, especially you have the computational part in it. If you didn't consider computation, then I believe for resolutions lower than 4K, and that is what the common test conditions for AV1 were. They're all less than 4K. At the time of the bitstream freeze, it was about 30% better than VP9, and today maybe closer to 35 to 40% better than VP9. So that's how it compares against VP9. Now we have different in the LibOM, which is sort of like the reference software. We have different speed settings that you can choose. So as you increase the speed level, then what happens is that gain is going to reduce. And roughly, if you go to speed 5, like 0 to 5 is like several steps. 5 is not quite real time, but getting there. Will be losing maybe 10%, but compared against VP9 again at the full resolution, at the full complexity. So I think that 35 to 40% still stays at the same complexity level as VP9. So I think that overlap area of the complex computation between VP9 and AV1 is relatively small, so it's not very easy to get a good feel for that. But I will let someone who has more experience on the real-time side to chime in also.
Maybe in 20 seconds, very quickly. During the standardization days, AV1 came in as one of the codecs where the compression savings are very noticeable at low resolution as well. Although in other standards like HEVC and even VVC as well, the gains started diminishing a little bit as you go to smaller resolution. The complexity question or the CPU cost is pretty hard to answer here.
Yeah, and I'll just jump in too with a comment because Visionular has done quite a bit of work, and where I want to focus is on the AMD versus Intel platforms, and this also is an important consideration just because the architecture of those two platforms is different. You have more cores, and some implementations are optimized to work in certain use cases maybe a little more efficiently on one platform than another. So I guess really the takeaway here is, and apologize, we don't have the time and can't really go into all the details, but if you go to AV1info.com, AV1info.com, there's some very, very good benchmarks comparing live performance on Intel-based architectures and then on AMD. So might be interesting to people as well. Okay, so it's 10:01. I guess we should stop here. As usual, this conversation could easily have gone on for another hour. So I want to thank everyone, starting with our panelists. So thank you, panelists, for joining us. And everyone who hung in to the end, really appreciate you. And I guess until next year, this is a continuously evolving landscape. So next year we'll be here talking about maybe a little bit of the same and some new things. So, all right. Thank you, everyone. Have a great day.
Thank you, Mark.
Thank you. Bye-bye.
Thank you. Hi. Thank you, everyone. Mark, Jan, Shawn, Debargha, and Tarek for an insightful discussion into video codec standards. I've definitely learned a thing or two, or just learned how little I know about video encoders and decoders. I hope everyone's enjoyed this talk and will stick around for more of the events and sessions happening today and tomorrow at RTE 2021.